Hi everyone, welcome to my YouTube channel. I am Shlok Kulkarni and in this video lecture I am going to solve questions from Descent chapter in Keith Williams' GenNav book. These questions are very important in that they are frequently asked in DGCA CPL exams, ATPL exams and even in airline written exams. So proper understanding of the concepts and ability to solve these numericals are crucial for scoring good marks and crossing the passing limit. So I have been doing this series of video lectures in which I have been solving questions from 1 in 60 rule chapter in Oxford, Keith Williams, R.K. Bali, the sample papers as well. So do watch that video lectures if you haven't yet. Do explore my channel. In this channel you will find many video lectures from different chapters covered from Keith Williams, R.K. Bali, Oxford, etc. And if you have any questions, if you want me to cover any important subject according to you, or if you want me to address any topic that you find difficult or challenging, let me know in the comment boxes of any of the videos, and I'll happily make a particular video for you. So now let's start with this lecture with a new question, question 31. If there is a 17 knot decrease in headwind, okay, a decrease in headwind means can also be expressed as increase in tailwind, right? Now we all know that whenever there is an increase in tailwind component, what problem ensues? Whenever there is an increase in tailwind component, the rate of descent of your aircraft automatically decreases. Your aircraft will tend to remain suspended in the atmosphere instead of continuing that descent along the 3-degree glide slope. So the solution to this problem is the pilot must deliberately increase his rate of descent, increase his rate of descent to the normal value. Okay, if the normal rate of descent required on that particular glide slope, that particular ground speed is, let's say, 500 feet per minute, and these tailwind conditions are leading you to fly at a ground speed of to fly at a rate of descent of less than 500 feet per minute, let's say 300 feet per minute, 350 feet per minute. So as a pilot, you will respond to that situation, right? You will decrease the engine power of your aircraft such that your true airspeed decreases, the lift component decreases, and as a result, you will increase the rate of descent from that 300 feet per minute value to a value which is required for that particular descent, which is 500 feet per minute. So you will decrease your engine power as much as needed to capture the normal rate of descent speed. Okay, so increase your rate of descent to the normal value, to the required value, to the normal value. Okay, so next, the change in rate of descent. By what value are you going to increase your rate of descent? So that change in rate of descent equals to 5 times change in the speed of your aircraft. So 5 times this change in speed. Now whenever there is increase in tailwind component, there will be increase in the ground speed of your aircraft. Okay, a tailwind is nothing but a push given from behind, right? So the ground speed of your aircraft will increase by 17 knots. True airspeed plus 17 knots. So I'm going to write here plus 17. So 5 into 17 is 85. So the rate of descent, the change in rate of descent will be plus 85 feet per minute. So that means the pilot of this aircraft will have to increase this rate of descent plus 85 feet per minute. Okay, 85 feet per minute. Next, 32. Aircraft is at flight level 350, has to arrive at flight level 80. Rate of descent is given to you. Ground speed is given to you. What is the distance from the DME station? Okay, so let's say this is your DME station. Here is your aircraft. Next. Okay, your aircraft is at flight level 350. DME is at flight level 80. That means you have to arrive over the DME station at flight level 80. Now, rate of descent, which is equal to change in height, okay, change in height made during your descent divided by the time taken. What is the speed of your aircraft? 276 knots. Speed equals to 276. Now, rate of descent equals to 1800 feet per minute. Change in height. You are descending from 35,000 to 8,000. So change in height is 27,000 divided by time taken. So time taken equals to 27,000 divided by 1800 is equal to 15 minutes, which is equal to 15 minutes. Now time equals to 15 minutes, speed equals to 276 knots. So distance will be equal to speed into time, 276 into 15 divided by 60. Convert that minutes into hours because speed is in terms of knots. Knots is nothing but nautical miles per hour. So 276 into 15 divided by 60 is 69. So that means you are at a distance of 69 nautical miles from the DME station. Next. Aircraft is flight level 390 and you have to arrive over the DME station at 7 flight level 70. Rate of descent is given, speed is given. You have to calculate descent. Okay, similar to the previous question. So this is your DME station. Here is your aircraft. Your aircraft is at 39,000 feet. DME, you have to arrive the DME station at 7,000 feet. Rate of descent 2,500 feet per minute. Rate of descent equals to change in height divided by time. Okay, so 2,500. Change in height 39,000 minus 7,000 is 32,000, right? Divided by time taken to descend that much. So time will be 32,000 divided by 2,500. So 32,000 divided by 2,500 is 12.8. That is 12 minutes 48 seconds. Next. Speed given is 248 knots. Speed is 248. Time is 12.8 minutes. So distance will be speed into time. That is 248 knots into 12.8 minutes divided by 60. Right? So 248 into 12.8, that is 52.9 or approximately 53 nautical miles. So aircraft is 53 nautical miles away from this DME station. Away from this DME station. Okay. 3. Before. What will be the rate of descent when flying down a 8% glide slope at a speed of 340 knots? So glide slope equals to tan theta into 100. So 8% glide slope equals to tan theta into 100. So tan theta equals to 8 divided by 100, that is 0.08. So tan theta will be equal to 0.08. So theta will be equal to tan inverse 0.08. If tan inverse 0.08 is 4.57. So theta equals to approximately 4.6 degree. So glide slope angle is 4.6. So rate of descent equals to glide slope angle into speed divided by 60. So 4.6 degree into speed 340 knots into 101.3 feet per minute divided by 60. So 4.6 into 340 into 101.3 divided by 60 is 2640 feet per minute. Next. Aircraft is at flight level 350. It crosses a VOR DME facility at flight level 110 and it is 100 miles away from the facility. Speed is given, what is rate of descent? So it's a VOR DME station, right? So the symbol for that is something like this. Next, this is your aircraft. Aircraft is at flight level 350, 35,000. VOR station is at 110, 11,000 feet. So you have to cross this VOR DME station at 11,000. 100 miles is the distance and speed is 335, 35 knots. Change in height. Now change in height 35,000 minus 11,000 is equal to 24,000 divided by time taken. Now you have speed, you know the distance, you can calculate time. Time equals to distance divided by speed. So 100 miles divided by speed of 335, that is equal to 17 minutes. Okay, so 24,000 divided by 17 is equal to 1411.7, 1412 feet per minute. Okay, so rate of descent is 1412 feet per minute. Next, task, course, winds are given. Descent is initiated at flight level 220 and it is completed at flight level 40. Distance to be covered during descent is 39. What is the approximate rate of descent? So rate of descent equals to change in height divided by the time taken to make that change. Now you are descending from 22,000 feet, correct, to 4,000 feet. That is equal to 18,000 change in height. Now time. To calculate time, you must know the speed of your aircraft, the ground speed, and the distance. We know the distance. We do not know the ground speed, but we can derive that ground speed from the information, from various pieces of information given to us. TAS, course, winds. Okay, let's put them in the CX. TAS. TAS is 197. Course is 240. And winds 180 at 30. So, ground speed. Check the values. TAS 197, 240, 180 at 30. So ground speed is approximately 180 knots. Okay. So speed 180 knots. Distance 39 nautical miles. So time will be distance by speed. So 39 miles divided by 180, that is equal to 18 minutes. So rate of descent equals to 18,000 divided by 13, that is equal to 1384.6 or 1385 feet per minute. By what amount must you change the rate of descent to meet an increase in headwind of 10 knots? Increase in headwind component always, I've done this many times, increase in headwind will be accompanied by increase in your rate of descent. Automatically increase in your rate of descent, excessive. So this is the problem. Okay. So the solution to this problem will be to control your rate of descent, to prevent it or to stop it from exceeding a particular normal limit. Okay. So the solution is the pilot must decrease his rate of descent. Okay. Now by what value will he decrease that rate of descent? So change in rate of descent equals to 5 multiplied by change in speed. So 5 multiplied by, now increase in headwind component of 10 knots means decrease in ground speed by 10 knots. So 5 into 10 minus 10. So that is minus 50 feet per minute. Okay, so the pilot will have to decrease his rate of descent by 50 feet per minute. Next, 38. What will be the rate of descent when glide slope is 12%? So slope equals to tan theta into 100. So 12% equals to tan theta into 100. So tan theta will be equal to 12 by 100, that is 0.12. Now rate of descent equals to your glide slope angle into speed in feet per minute divided by 60. Now here the glide slope angle is how much? Theta, that is angle will be tan inverse 0.12, that is equal to shift tan inverse 0.12, 6.8 degrees. Rate of descent equals to 6.8 degree into 150 knots into 101.3 divided by 60. 6.8 into 101.3 into 150 divided by 60 is 1722. So rate of descent is 1722 feet per minute.